Hello everyone, today let's solve the problem number 98, valid binary search tree, right? So what the question states here, given the root of the binary tree, we have to return if it is valid binary search tree or not. So here we have been given root, we have to just find this one, whether it is a valid binary search tree or not, right? So a valid binary search tree is defined as follows. First thing here is the left subtree of a node contains only nodes with keys less than the nodes key. So you can clearly see here this one they are speaking of the left subtree, right? This one. So the right subtree of a node contains only nodes with the keys greater than nodes key, right? This is fine, right? Binary search tree they have given here. So binary search tree here in this case, we know one thing, if we are considering this one as parent or this one is root, right? So just give me a second. So if we have considered this one, the left subtree value, this one, this should be lesser than the root value, and the right subtree's value, this should be greater than the root's value, right? So both the left and right subtrees must also be a binary search trees. So these are the three things that we need to keep in mind to be a valid BST, right? So just let's come to the first example here in this case. So in this case we have 2, 1, 3. So 1 is less than 2 and 3 is greater than 2 here. In this case this is valid, right? So we will return true. So let's come to the second case here. So just give me a second here. So let's come to the second example here. So here we have root equals 514 null null 36. 514 null null 36. Here you can clearly see we don't have here anything, so they have considered null null. This is fine for the input. 3 and 6 we have. So here you can clearly see 1 is less than 5 and 4 is also less than 5. 4 should be greater than 5 to be valid binary search tree. First thing, here itself it fails, right? So let's not move further here. This one we have to return false in this case. This is fine. So I hope these two examples are completely clear, right? So I hope the question is completely clear. They have given wonderful examples just for the sake of understanding purpose. So and I hope the question is completely clear, and what we need to do is completely clear as well. Let's discuss the approach followed by the edge cases one by one, and then finally write the code and discuss the complexities for the code that we have written. Initially, let's discuss the approach first. So the first thing that we need to keep in mind here is we are going with a recursion or recursive min-max approach, right? So we are going with DFS and min-max approach, recursive DFS or recursive min-max approach we can call, right? So just keep in mind we are going with the recursive DFS or recursion, right? So I have considered the first example, the same example that they have given given in the question. First example that they have given in the question. So root here 2, 1, 3 we have. So 2, 1, 3. This satisfies all the condition to be a BST, right? So this is lesser, the value is lesser than the root node. This one, right subtree, the value is greater than the root node here. This one, fine. So this is said to be true. In this case, if it satisfies all the condition to be a BST, valid BST, then we will have to return true. So the output will be quite obviously true in this case, right? So let's move on with the this one, step-by-step explanation. So the first step here is we will start at the 2 here. You can clearly see we will be starting at 2 here in this case. This is fine. So min, we will assign this one to the long dot min value, and max, we will assign this one to the long dot max underscore value. This is fine, easy, right? We will check if 2 lies within the min comma max. Yes, 2 lies within the min comma max. We know this one, right? So let's move on with the second step here. Left subtree of 2. So we have to check for left subtree of 2 and right subtree of 2, right? First we will check for left subtree of 2. So we will move to 1, nothing but left child of 2. We will move to 1, nothing but this is the left child, right? This is left subtree and this is right subtree. So I am speaking of this one. This is left child of 2 here. We will move to 1, nothing but left child of 2 with min equals long dot min underscore value and max equals 2. We will check if 1 lies within min comma 2. Yes, it does, right? So let's move on with the next step here. So step 3 here. In this case, this is right subtree of 2. So we have already checked for left subtree of 2. Now we will be checking for right subtree of 2. So we will move to 3. When I say we will move to 3, I am speaking of this one. We will move to 3, right subtree of 2, right? So this is fine. Right child of 2 with min equals 2. Now we have min equals 2 and max equals long dot max underscore value. This is fine. We will check if 3 lies within 2 comma max? Yes, it does. Through 3 lies within, we'll check if 3 lies within 2 comma max. Yes, it does, right? So it satisfies all the condition. In this case, we will be returning true, or we have to return true in this case, right? So the output that we got here is true, and the output that they have given for the question one, example one in the question is also true, right? So this is equivalent to the output that they have given for the output that we got is equivalent to the output that they have given for the example one in the question. So approach works absolutely correct in this case. So here now we are familiar with the approach. As we are familiar with the approach, let's discuss the edge cases quickly. So when I say edge cases, so the first thing that we are considering here is single node tree. So we have only one node here. We have only one node. Quite obviously, we will return true in that case. So this is base case. Just remember this one, right? We have only one node here. So we will return true in this case. So let's move on with the second edge case here. Only subtree invalid. Only left subtree invalid here in this case. 5, 4, 6 we have. This is fine. Null we have 3, 7. Right. So here only left tree invalid. In this case, we will be returning false. Left subtree invalid. Right. So in this case, we will return false. So only right subtree invalid we have already considered for the left subtree. You can just draw the same way, the first tree, and you can just check. So in this case, we will be getting false. Right. Let's move on with the final edge case or the fourth edge case. Just give me a second here. So yeah. Let's move on with the final edge case here. All nodes same value. When I say all nodes same value, we have 1, 1, 1 here, right? So we have 1, 1, 1 here. So to be a valid BST, so the left subtree has to have the value lesser than the root node, this one, right? And the right subtree should have the value greater than the root node. In this case, this miserably fails, right? Every value is same here in this case. So the output is false here in this case, right? So these are the 4 edge cases that we need to consider here, right? So the first edge case is for the single node tree. The second edge case is for the only left subtree invalid, and the third edge case is for the only right subtree invalid, and the fourth edge case is for the long all nodes same value, right? So I hope the edge cases are completely clear. So now we are completely familiar with the approach as well as the edge cases. As we are familiar with the approach and edge cases, it will be easier to write the code. Let's start writing the code now. So now let's start writing the code. Let me clean up this one. Just give me a second here. So first step we need to keep in mind here is, so here we will start the validation with the full range of possible values. We have discussed this one in the approach already. So I'll just return here. In this case, we'll be making use of the helper function. Let's write the helper function first, then we'll make use of the same helper function here, right? So I'll just go with the helper function to validate the binary search tree this one properly, right? So we'll be doing that recursively. So I'll quickly write here private boolean. So this one, let me give validate of tree node here in this case. Let me just give me a second here. So this is fine, node, and I'll just give long min and long I'll just give here max. This is fine. So first step here is base case. We know the base case. An empty node is always valid. We have discussed this one. An empty node or leaf is always valid, right? So I'll just I can write on this way. If node equals null, then what we will do? We will return true in that case. So because it is valid, right? An empty node is always valid. So we will return true in that case. So if the node is out of the valid range, then it is false. Then we have to return false. So I'll just give here if value of the node is less than or equal to min here, or if the value of the node is greater than or equal to max here, in this case what we will do? We will return false. This is fine. So the next step here is we have to recursively check the this one left and right subtrees. We are going with the recursion. We have I have said this one during the approach, and we have already discussed the approach. We know this one, right? So we will recursively check the left and right subtrees. For the left subtree, value must be in the range, nothing but min comma value of the node, and for the right subtree also values must be in the range. Nothing but node comma val comma value of the node comma max. We know this one, right? So I'll just give here return. So validate, as we are going with the recursion, this is function name valid. I should have copied this one. This is fine. Validate node dot left here in this case comma min and node comma val here. This is fine. So let me copy this one in this case. Let me make use of here. Let me paste. Sorry, what did I do? I've just copied this text right here. Let me paste it over here. Validate. So this will be node dot right here in this case, node dot val in this case. This is fine, and finally max. This is fine. So this is it for the function validate. So let's come to the main function. So I said we'll be making use of the helper function validate inside this one, right? So what we have to do here, we have to start the validation with the full range of possible values. Full range of possible values means max and min. Long dot max underscore value, long dot min underscore value, if you remember, right? So first let me go with the root. So let me do one thing here. So we have to make use of the function name, right? I have already copied this one. Let me give validate here. So first thing is we will start from the root, and second thing is let me go with long dot min underscore value. So this is fine. So same thing, let me copy here this one. I'll change this one to max instead of min. So let me paste it over here. This one I'll just give long dot max underscore value. This is fine. So I'll do one thing here. I'll just give the semicolon here, right? So let me format the code once and let me hit the run button. This has to work. Let's see. So here, let me enlarge this one. Yeah, you can clearly see here the sample test cases are getting passed. So let me hit the submit button quickly. Let's see whether this works for all the test cases or not. So yeah, you can clearly see here all the test cases are getting passed. Means the code works absolutely correct on this case, right? So let's quickly discuss the complexities for the code that we have written. So the approach that we went with here is recursive min max, or we can just call this one recursive BST validation, DFS with min max range check, right? So this is fine. So overall time complexity would be here in this case, it would be big of n. Why it is big of n here? Because we are processing or we are visiting each node exactly once. That performs a constant amount of work per node. So overall complexity would be big of n. So what would be the space complexity here? Overall space complexity would be big of h. Why it is big of h? Because we are making use of the recursive call stack, right? So we are making use of the recursion. We know this one. So as we are making use of the recursive call stack, so the recursive call stack depth is at most the height of the tree. We know this one. Nothing but h, which is basically big of logarithmic n for the balanced trees and big of n for the skewed trees. Skewed tree means whether if it can be left skewed tree or right skewed tree, right? So we have discussed this one in the previous problems in the edge cases many times. By this time we have to know what is left skewed tree, right skewed tree, BFS, DFS, and we have to know that the tree problem can be solved in either BFS or DFS, every problem, right? So these are the certain things we have to know at any cost, right? So the recursive call stack depth is at most the height of the tree h, which is logarithmic n for the balanced trees and big of n for the skewed trees. We will be going with the height of the tree itself, right? So we don't have to give logarithmic n or big of n. So we'll just consider the recursive call stack, this one call stack depth, right, is nothing but it is the height of the tree. Let's go with big of h in this case. So overall space complexity would be big of h here. So the time complexity is big of n and the space complexity is big of h for the code that we have written. So I hope the complexities are clear. I hope whatever the code that we have written is completely clear as well, right? For now, this is it. Thanks for watching, guys.